This morning I woke up with a question on my WhatsApp by one of my students about thermal expansion coefficients, and it reminded me of my early days when I was a student. The relation between them were very intriguing to me, and later on I went on exploring about whether length can be explored with the help of numbers or not, and understanding more deeply why the whole physical experience is referred to as Maya. But, anyways, this is a very simple relation. This is first we need to understand the definition of thermal expansion coefficients. So, we have suppose this is a cuboidal block at temperature T, and let's consider one of the lengths, this length, and let's call this Li, so initial length. And then you heat it up a little bit, the temperature increases from T to T plus Tt. This increase in temperature is taken very less because you will understand why. And then suppose this is Lf. So at the higher temperature, the length is now a final length. This is Lf. So this relation, the final length is written as length, initial length into 1 plus alpha dt. Just break it up a little bit and you will understand. So final length is obviously greater than the initial length, so it is something Li plus something, and this increase in length, as you can see, is proportional to how much the change in temperature was dt and how much length we began with, and this is a constant here, alpha. So of course, the increase in length will depend on how much length we start with, because if we start with the longer length, the increase will be longer, and if we increase the temperature too much, the increase in length will be longer, right? So this term here comes, this is increase in length, and here comes the alpha. And why this increase in temperature is taken to be small dt, because if you heat something over a large range of temperature, let's say from 300 degrees Celsius to 500 degrees Celsius, then this alpha could be varying in this time interval. So it might, like for 300 to 400 degrees C, or maybe let's say smaller, 300 to, yeah, but that's fine, 300 to 400 degrees Celsius, it increased at a different rate, and after that the rate of increment become faster. So more increment in length, more increase in length here, this can happen, right? So to make it a uniform number, we can assume the temperature, the change in temperature is not so much. Okay, so that is the definition of alpha. From alpha, we can reach to beta. Now, what is beta? So now we are thinking about this area, as you can see, and this area is composed of two lengths. So length into breadth. So this is Li, the length, and let's say this is the breadth. It's a product of Li and Bi. And then if you heat it, then the area increases. Let's say now the area is AF, and the final lengths we can find out from the previous relation. So it seems very tempting that we can figure out the relation between alpha and beta. Now what is beta? So beta will be defined in the same way as alpha has been defined. So this is your AF, final area is initial area into 1 plus beta dt. So you can break it up and you can understand how, what it means. So final area is greater than AI, and this is the increase in area, which is of course proportional to the initial area and change in temperature, and then there is a constant beta. But it seems very tempting because we can figure it out using the previous relation, the expansion in length. So because AF is final area is LF into BF, and then you know that the final length should be like this and the final breadth should be like this. Same alpha will be used in both of them, right? So we know these relations, we can multiply them and we can find out the final area, and it turns out that Li and Bi gets separately multiplied here, and this term gets squared. So you have 1 plus alpha dt whole squared. When you open it up, LIBI becomes the initial area, right? And when you open this part up, you get this thing. And now in this thing, like this is where many students get stuck, because this term here needs to be ignored. This is a very small term, and the change in temperature is very small, as we have assumed before. So should be ignored to get to the relation which is written in many textbooks. So if we ignore this term, then only you will reach to this thing, that the final area is initial area times 1 plus 2 alpha dt. And now if you compare it from the um, definition, this is your definition of beta, you compare it from here, and you can understand that beta is equal to 2 alpha, right? So this is interesting because many students want to prove this thing, and this is here because when we are young, we don't like to approximate things, and it's only after you get a little bit of experience of engineering or science, then you understand the importance of approximation. I see that in calculus there is an inherent approximation always. So at some point of time, I didn't like calculus that much because it wasn't considered by me. I couldn't take it as true knowledge. But anyways, we need to understand approximations also to understand, to simplify certain relations. Similarly, you can prove that the volume and volume expansion coefficient gamma is 3 alpha, and you will have to use these approximations also, and there you will encounter this cubic term 1 plus alpha dt, which you can open it up like this, and these terms will be small because dt is small, so dt squared will be very small. Oh, I'm so sorry, I didn't explain it before. If dt is small, dt square is very small, right? You can take certain examples. Let's say 0.1 is a small number, and you square it, 0.1 square, you can figure it out, 0.01, even smaller. So if dt is small, dt square is very small, and dt cube is very, very small, even smaller, right? Even smaller. So you can ignore these terms here, and then you can approximate, and you will see that in place of gamma, you will have 3 alpha. So this can also be done. One very interesting question I would like to put here to the viewers, which made me thinking for days when I was a child, a young boy. And that was, suppose that this is some metallic disc with a hole in the center, and this is the diameter of the hole. What would happen when you heat this disc? What will happen to the diameter of the hole? Will the diameter of the hole increase or decrease? On heating this disc, the diameter of the hole will increase or decrease. It can be very counterintuitive and very funny. It will be very interesting to explore. You can do experiments also and see what happens. But as a young student, I never wanted to do any experiment. I wanted to reach the answers through theoretical ideas. So best of luck thinking about this question. Thank you very much for watching.